What's going on, everybody? It is Kistner again, and today we're going right into our second to last topic of the semester. If you're watching this in 2017 with me, it's section 4.1, topic 4 out of your book, and eventually we're going to get to page 92 in your student companion if you're following along in there. But first, we'll look at a few definitions and get us prepared so we can do example 1 on page 92. So let's turn the page, let's get there, and let's get going. So the first question this is going to ask us is, does this table represent a value, table of values represent an inverse variation? Well, this word inverse variation we have never heard before, so let's look at what that means. Down here it says an inverse variation is a relation between two variables such that as one variable increases, the other decreases proportionally. Now, three things are happening. You got one variable increasing, other decreasing, and then this word proportionally is very important. For the table to represent an inverse variation, the product of an x and y must be constant. That's the proportional thing. And we're going to look at that in just a second. But let's check off the other two first. We need one variable increasing. Well, here it looks like x is always increasing. It's not increasing the same amount every time, you know, plus 1, plus 1, plus 1, plus 2, plus 6. But it's still increasing every time, so that's all that matters. My other variable should be decreasing, and it is 12, 6, 4, 3, 2, 1. It is decreasing. So proportionally, the way we check that is we multiply the two variables together, x times y. You should get the same number every time. If only one number is different, you don't have inverse variation. So 1 times 12 is 12, 2 times 6 is 12, 3 times 4 is 12, and so forth. That means, and you notice that all of them end up being 12. And down here it says, since the product of the value is constant, the table of values represents an inverse variation, and therefore we have what we were looking for originally. So let's do one ourselves. You'll need a calculator, and this will be example 1 on page 92. Determine if the table of values represents an inverse variation. Fill in the table to help. Well, the first thing we need to check without a calculator is one variable increasing and is one variable decreasing. 1, 2, 3, 5, 6, 15, increasing. 25, 25.5, 12.75, 8, 5, 4, 1. That is decreasing. So yes, the first two things are met. So let's get a calculator out and check the rest of it. So when we get our calculators, and obviously the first one here, 1 times 25.5, that's going to give me, let me redo those. My pen jumped around. That's going to give me 25.5, clearly, because 1 times 25.5 is 25.5. So all these other boxes need to be 25.5, or I do not have an inverse variation. So in our calculator, I'm going to do 2 times 12.75, and I get 25.5. That's right. Then I'm going to do 3 times 8.5. That's also 25.5. 5 times 5.1. That's 25.5. Now, if you notice, all of these so far are 25.5. So it's sometimes we'll assume that the rest of them will be as well. But you can't do that. If just one of these is not 25.5, we don't have an inverse variation. So we have to check them all. So 6 times 4.25 is also 25.5. And the last one was 15 times 1.7, which is also 25.5. So yes, they all end up being 25.5. So we would say, yes, this is an inverse variation. Okay, yes, this is an inverse variation. The x is increase, the y is decrease, and the x times y is all constant. And that's what we did down here in this row, is x times y. All right, so we'll do part B in class. Let's go ahead and turn and actually get the definition of an inverse variation. Inverse function. Inverse variation. When a relation between x and y is an inverse variation, we say that x varies inversely as y. You'll hear me say that a lot. X varies inversely as y. Inverse variation is modeled by the equation, and you should know this equation. This is a very important equation. Y equals k over x. Y equals k over x. So what that means is over here, we could model this situation as y equals k over x. Now, the only thing we don't know in this equation is k. Y and x we have. X would be 1, y would be 25.5. X would be 2, y would be 12.75. X would be 3, y would be 8.5. So if we took the time right here and solve for it, let's just plug in the first one. If y is 25.5 and it's k over 1, you multiply 1 on both sides to get rid of it over here, and you find out that k is 25.5. And k is what we're going to call a constant. That's what it says over here. The variable k represents the constant of variation, the number that relates to two variables in inverse variation. So in this table, the constant variation is 24. If you notice, the k is when you multiply. 1 times 24 is 24. 2 times 12 is 24. 3 times 8 is 24. So this is just x times y, also known as k. So over here, this bottom number, when I multiplied x times y, became my k, and I now know that this variation, it didn't ask me to do it, it's just this. This is the variations equation. We just wrote an equation for it, which is going to be very useful when we go to model and do those word problems. Alright, so let's look at number 2. In an inverse variation, x equals 6 and y equals 1/2. What is the equation that represents the inverse variation? Well, we know it's an inverse variation, so we can start off by writing y equals k over x. That's the definition of an inverse variation. That's the equation. And we plug in x and y and we solve. We're going to get 1/2 equals k over 6. Y equals 1/2, x equals 6. Multiply by 6 on both sides. The 6's cancel. You're going to get 3 equals k. Now that means our final equation is y equals 3 over x. Just solving for k is not the final answer. You have to plug it back into the inverse variation. Okay. Part B is going to extend this. If you want to go ahead and try it, it says, what is the value of y when x equals 15? You simply just plug in 15 for x, and you'll get y. It's pretty obvious what that's going to be. Now, moving on to example 3. So the amount of time it takes for an ice cube to melt varies inversely to the air temperature in degrees. So it varies inversely. So we know we have y equals k over x. We're going to use that form because it's inverse. At 20 degrees Celsius, it will melt in 20 minutes. How long will it take the ice to melt if the temperature is 30 degrees Celsius? So one thing we missed back here, well, I didn't miss it, I just didn't mention it, is you can rework this equation all different kinds of ways. Y equals k over x can become x equals k over y. You just multiply by x, divide by y. Or x times y equals k. That's what I just wrote here, where k equals 0. Now, over here, they don't define what x and y is. What's okay about it is we can define it ourselves. If I let degrees be x and time be y, we'll get an equation that we can plug in. So at 20 degrees Celsius, the ice melts in 20 minutes. So when y is 20, x is also 20. And we're trying to solve for k. So you multiply both sides by 20. 20's cancel. You get 400 equals k. Alright? So that means my equation is now y equals 400 over x. And we just go back in and plug in 30 degrees for my x. So I'm going to get y equals 400 over 30. And in our calculators, well, obviously the zeros will cancel and we get 40 over 3. And I think that's going to be the final answer. 40 over 3 minutes is what that would be. And let me check to see what your book actually left it as. Okay, they actually went ahead and rounded that. So they went ahead and typed into their calculators 40 divided by 3. And it says it's about 13.3 minutes. Now don't say it equals that, because it definitely doesn't equal that. It's 13.3333333 all the way. But it's really about 13.3 minutes. Okay? But if we'd have switched those, we'd have gotten the same answer. We'd have switched what degrees were and what x and what x and y was, we would have gotten the same answer. So that doesn't matter, as long as you know the general form of an inverse variation is y equals k over x. All right. The reciprocal function. I want you to watch this and write this stuff down somewhere. This is not something that you can put into your student companion. There's not a place for it, but you need to see this. You need to learn this. This thing called the reciprocal function maps every non-zero real number to its reciprocal. So if you have 2, the reciprocal function makes it 1 over 2. If you have, here, let me write this out a little bit. If you have 2, it becomes 1 over 2. It becomes its reciprocal. If you have 3, it becomes 1 over 3. So we're going to have to figure out what that function is in a second. But 4 would become 1 over 4. Okay? Well, there's some things we need to know about the reciprocal function. The first one is the domain is x is such that x is not 0. That means it's all real numbers except 0. Okay? So what can not be 0? Well, the denominator cannot be 0. So that tells me that my function probably has this shape to it, or this design to it. Y equals 1 over x. X can't be 0. If you look, you plug in 4 for x, you get 1 over 4. 3 for x, 1 over 3. 2 for x, 1 over 2. Okay, this is going to be the reciprocal function right here. And the range cannot be 0 because you aren't ever going to divide by 0. You're always dividing into 1. So the only way that y could be 0 is if the top was 0, and the top will never be 0. That's your domain and range. Okay? You also need to know how to do it. We can use a table of values or technology to graph this function. So you could type this into your calculator. You can go into y equals and let me clear out what I have and make sure my plots aren't on and all that stuff. But I'm going to type in 1 divided by x. And I'm going to hit zoom 6 to take me to where I need to be. And it looks like that. That's something weird right there. That looks really, really weird. But if you notice, if I go to my second graph and I hit my table, I get these same values. And let me show you. Negative 3 gives me negative 33333, which is negative 1/3. Negative 2 gives me negative 1/2. Negative 1 gives me negative 1. And that's what's happening over here in the calculator. Okay, so you could easily graph this function. It'll end up looking like that, like we just did, if you notice. At negative 1, I'm at negative 1. At negative 2, I'm at negative 1/2. At negative 3, I'm at negative 1/3. Okay. At 0, notice I don't hit that at all. This line goes up forever this way, and it goes down forever this way. This looks really weird. It's like a piecewise almost. But at 1/3, I'm up here at 3. At 1/2, I'm up here at 2. And we'll talk about why that happens in class. At 1, I'm at 1. 2, I'm back at 1/2. 3, I'm at 1/3 again. So if I just plot these points, I get this shape, and it just kind of fills itself in. And we're going to talk about why it never touches the x-axis or the y-axis. We will talk about that. Okay? But make sure you go back through and watch this section again, because this is a very important thing to lead us into what I'm going to show you at the bottom of this page in class. Other than that, make sure you've done everything that I've assigned, and this is Kistner out.